Hello everyone, in this video we'll start with a new software, and the software is Slide. We are going now to talk about slope stability. Slope stability is one of the most important application for geotechnical engineering. No one in geotechnical engineering hasn't analyzed a slope stability before, either in 2D or 3D. In our videos, we will try to mention different ways to analyze the slope stability in different softwares and different techniques between the limit equilibrium analysis and the strength reduction method. And we will try to understand the difference between both of them. In today's video, we will try to analyze one important slope stability problem, and we will try to compare between different software to see, and between different technique, either in 2D or 3D, or between limit equilibrium analysis or strength reduction method. And we will try to talk about and to tackle the techniques to improve the factor of safety and to optimize our solution. So here we will start in AutoCAD to see the dimension of our problem. So our slope will be, as we can see here, we will have like the base will be as we can see here 30 meters, and we will go up here like 15 meters. Then we'll go here to 15 meters, and our slope will be 2 in horizontal direction and 1 in the lateral direction, and our slope height is 5 meters. So if I did this like 5 meters and I did offset 5 meter, and this is in the vertical direction. So in the horizontal direction, I will take 10 meters and I will go up here. And now I will end my slope. So this is going to be my problem. And as we can see here, the slope head here will be, we'll add here 15 meters, and this will be our problem. So this one will increase to here. So this is dimension. If we add it list, we can see that this is 40 meters now, or we can go to dimensions. This dimension is 20 meters, 40 meters, 15 meters, and this is our problem we will try to analyze. So now we will go to our software called Slide, and we will start with Slide. Slide is a software for as a use limit equilibrium approach to analyze the slope stability. In order to model your problem in a Slide, we will start from these toolbars, which gives you some commands and some tools which enable you to model your problem. So here we will go to draw polygon, and you can go here to edit or view and start to add your grid. So I will start with this grid, and I will choose the color to be red, and I will make it 1 and 1 in both direction. As we can see here, it's not appearing pretty well, so I will go back and I will show it here, and I say okay, but now it's bit like doesn't appear pretty well, so I will go back here to view, and I show grid, and I will choose different ways to view it, as we can see now. So I will start with drawing my problem with here. We can, if we went back here to view grid, we can see that sorry, if we went back here, we can show snap and limits. So this limits means the limits of your window here. So in X direction, we need 40 meters, and let's say the minimum to be -1 to just have a bit domain here. And sorry, for the minimum will be minus 1, and here will be in X will be 45, and in Y to be 25. And I will say OK. As we can see, our problem has modified from 0 and 0 to 20. So I will start here with drawing. Here, if you look at the right hand side at the bottom, you can find that the coordinate has changed into 0 and 0. So I will start with drawing my 40 meter, and I start to complete here with 15 meter. So you can see here, this is 15, this is 16, this is 15, and I can go here to another 15 up to 25, and I can go here by 10 meter up to 15 and up until 20 here, and I go back here to 0 and 0 again, sorry. So here I go until 20, then I complete until 25, then I go down to 25 and 15, then I end here at 40, and I say enter. It's very important to add enter. So here I will start to draw polygon. So and I will go now to boundary, and I will start to add the external boundary. So now this is my problem, and I can add different layer here if I started to add the material boundary to divide this. So I can choose this part here, and I can change the material. So if I went here to boundary and I started to add material, so if I went to properties and define material, so I can find that I will have a sand layer, and here you can choose the different soil model to define your model between undrained and more column. I will use more column here, and the unit weight will be 19, and cohesion 1 and friction angle will be 32, and there is no water surface, and I will say okay. And for the second layer, to say it's clay, and I will add cohesion to be 30 and phi will be 0, and I will add this to be 15.5, and I will say okay. So if I just checked here and I added if I just checked here and I went to convert boundary to material boundary, and I came here to assign material to be clay, and this material assign material to be sand. So as we can see here, the bottom material is clay and the top material is sand, and we will see how we can verify and can make some different cases to see the slope, how it's gonna fail. But for the beginning, I will just add one material. So I will assign the material to be sand as one material. Important thing, you have to go here to view. If you want here to view, this is limit, this is gray, this is snap, and this is very important things you have to take into account when you are doing your analysis. And boundary, we already added the boundary, we are not considering water. And for load, we can add load here, and this load will be 10 kVA, and it will be okay. So I will add it from here to here. Then I will go to support, not now, and I will surface option. If I went to surface option, I will find that he's creating that the surface option is circular. There are different ways to define the failure of the surface. You may make it not circular or circular. I will choose it circular. And you can choose the grid increment, and you can even choose the default values. You can look at this step by step. And if you went back here to surface and you started to add auto grid, he will say error cannot define the auto grid failure, and this is because we have to check if the failure will be from left to right, as in our case, or from right to left. So to check this, we have to go back to view, preference. You have to go to boundary analysis, sorry, project setting. If you want to project setting, we can see here it's defined from right to left, and that's wrong. It's from left to right. And the unit, as we can see here, it's metric, and for time days, and for permeability, because this software can work on infiltration and other ways. You can choose the method for solving your problem. I will use Bishop simplified, and I will use Spencer, and will keep Japanese simplified as well. And I will say OK. I will go back here to surface and I choose auto grid, and he will divide my grids into 20 by 20. And now our model is complete. I will just save it here in desktop, and I will say save. Now I will go to compute. He computed it. Now I interp and I see the factor of safety from the results. We can see now this is the factor of safety is 1.489, and we can see that this is the most critical surface for the failure. If we started to add, like to show more about this, so this is other different failure surfaces. This is all the failure surfaces, and we can come here and show this, and we can select here like this strip, and he will start to give you all the information about this is the vertical load, and this is the lateral forces, and this is the friction at the base and the equilibrium between them. That's why we call it limit equilibrium analysis, and this is from Bishop. Let's see other. So this is the factor of safety from Spencer. It will be almost say it's the same as Bishop. And for Jambu simplified, it's less. You can view your results, and you can show all your results here in in the way you want to take your output. So I will go back to the problem here, and this is the case of static load. So let's imagine we have a dynamic load as well. So I will go here to loading, and I will add seismic load. And the seismic load will add it as a pseudostatic way. In the pseudostatic way, we add the horizontal to be 0.2 G, and we say OK. So the seismic force is the slice weight is multiplied by seismic load coefficient, which is zero point 0.2, and he increases this. So I expect the factor of safety, as we can see here, will decrease. If I computed this and I want to see the results, now I expect the results will decrease. Yes, so now the factor of safety had decreased to less than 1. So it expected this failure, this surface will fail. In order to improve this, we can go here to do some soil nailing. So if I added support pattern here, I will start to add it normal to the boundary. And I want its length to be 5 meter, and I want the distance between it to be 1.5 meter. And I say, okay, so I choose this until here, and this will be my soil nailing. If I started to run this analysis again, and I showed here the uh, factor of safety, we can see that before the factor of safety was here, but because we cut this area with the soil nailing, now we have improved the soil through this nailing by cutting the shear surface, and this is the critical failure surface, and it's 1.8. So to be able to see now, this is the forces here, you can see it, and even you can see the forces in this soil nailing. So if we went here and we can see its value as well, so its value is 100. And its tension, of course, and its tension. As we can see here, he refers it as its tension. So this is an introduction about slide. We can go back here and we can remove this, and we can delete the seismic load. And we remember the factor of safety was 1.48, so it was safe. Let's imagine we are going to go here to add another boundary. So we will go here to add boundary material. So we will imagine that there is a clay material here, and we will assign a different material here. So this is the clay material is weak material. So let's see the effect of adding this layer of clay here. What will be the factor of safety? So as we can see here that the failure surface has moved here, and the factor of safety has increased because this is the failure will be here. So let's go back and we change the properties of the material clay, and we're gonna make it 10, and we say okay, and we run this again and we show the results. So we see that when we decrease the shear strength of the material, it has decreased to 0.85. So in order to increase this, and even if I use the Spencer, it's less, and this is 0.7. And we didn't even include the um, the seismic load. So in order to support this, we go to soil nailing here, and I make the spacing to be 1 meter, and the length will be 5 meters. That's enough. And I will say okay, and I will start to add them from here to here. And I even don't need all of this. I can make them 4 meters only, and I say okay. If I ran this analysis now, let's see how the factor of safety modified. Now we can see since we cut this part, there is a support here, and now the factor of safety has increased due to supporting this part of the weak clay through this soil nailing. And looking at the forces here, we can see this is the pre-tension force inside the soil nailing. So you can modify whatever you want and you can do many things. Let's imagine adding another seismic load here, which will be um, zero point 0.2, and we run this analysis again to see the factor of safety. So we see it's barely 1, and this is the weak part here. So this is an introduction about slide, and I'm leaving you with the software, and hopefully you got an idea about how to calculate the slope stability using the limit equilibrium method using slide. Thank you. See you in next tutorial. Bye bye.